Stephen Goodman. I'm part of the Aqua team. I represent Sonia and Sergi, who's not here. We're going to go through all the things we've covered up to date in this lab. Some of the things that I'll be going over, we'll have the introduction, the background. We'll just briefly touch on these things right here. We have briefly touch on the introduction, SSOC, and our step response. I think we've flogged that dead horse. And then we'll cover a little bit more in depth in the sign response, the experiment, and the model. And then we'll draw some results and finally some conclusions. Here's our system. You just saw it on Will, and Trent's presentation. So I won't spend too much time lingering on this. Our system block diagram. Again, our manipulated variable is our input percent, and then output is our control variable, which is in amps. This is an example of our steady state operating curve. We broke this up into 3 different regions. Again, I'll point these out. We had a desired output range of 0.5 to 2 amps. So up here we have our upper region, which is 1.5 to 2 amps. Our middle region, which is 1 to 1.5, and then finally our lower region, which is 0.5 to 1 amp. This is an example of our step response. This is our mid-range. You can see here that we started out with an input percent of 50. We stepped up 2.5% to 52.5, and this is the resulting output. The results of our step response. We got the average. For our gain, we had 40 plus or minus 13 milliamps per percent. Dead time was 110 milliseconds, and response time was 107 milliseconds. This is the FOPDT model we applied to our step response. Again, it was for the same range that you saw the example. Input starting at 50%, stepping up to 52.5, and we fit our model to our data. This was the results of our FOPDT modeling. We had 30 milliamps per percent. Dead time was 90 milliseconds. And response time is 150 milliseconds. This closely agrees with our experimental data. So then we move on to our frequency response. This is an example of our high range frequency response. You can see the transients and the overshoot, and then settling out here to steady state. This is how we calculated our phase angle and amplitude ratio for our frequency response. The amplitude ratio is calculated similarly to gain, delta C over delta M. And then phase angle is little t over big T, which little t was the difference between the 2 peaks of the input and the output. And then big T is from peak to peak of the input. So we took that and then put it into a Bodie plot, and then calculated our FU, which was 9 cycles per second. Our K value was 0.045 amps per percent. We had 1 over KCU, which was 0.018% per amp. Our order we found to be roughly about 0.7 for this range. And this is where our phase angle was equal to negative 180 degrees. So the results from our Bodie plot. We don't have sufficient data for our low range, so our mid-range, see these both agree here fairly closely. Again, for our dead time, close correlation between the two. Again, for our response time. Critical gain, this is the KCU value. You can see here they were both 0.02 for both both mid and high range. And then our ultimate frequency, we had some variance here. Our middle range was 4 cycles per second, where our higher was 9 cycles per second. higher frequencies that you noted in Will and the chocolate team's presentation. So here's a Bodie plot model for our low range. Here's for our middle range. You can see that the model fit the data pretty well. There wasn't a whole lot of deviation. For our high range, again, we got a pretty good fit on our model. This is, like I was describing, the variance in the higher frequencies seems as you go up, the more variance you get. Sign model results. You see there's some variance here in the calculated dead time. Response time, we also got some variances. However, our gain seems to be pretty dead on. Here's the results from our frequency response. So our experimental data, you'll notice that they match up pretty well, both here on response time and gain. Our dead time, I noticed that they were calculated wrong about 30 minutes before this presentation. So when I went through and calculated, I noted that our dead time was about 0.03, which correlates fairly well to the model results as well. Comparing the step response to our frequency response. Again, our gains correlate pretty well, response time, and then our dead time, again, was 0.03 that was calculated. So there's a little bit of variance in the dead time when we compare step response to frequency response. So in conclusion, for our operating range, we found that 32% to 70% input satisfied our customers' wants of 0.5 to 2 amps. We found that our system was approximately first order. Our ultimate frequency was 6.5 cycles per second average. Our KCU value was roughly 50 amps per percent. And as you can see here, our order was 0.9.